Hi, my name is Sebastian Matteau and welcome back to this fourth and final video tutorial in the series on deep learning with Keras in Python. In the previous tutorial we saw how you can use a deep neural network, a pre-trained deep neural network, to classify an image, and we classified the bunny and the neural network felt it was a chichu. What we're going to do now in this tutorial is basically build on that and use that same neural network, MobileNetV2, but now modify it slightly and train it to perform a slightly different task than the task that it was originally trained on. And this is a form of what is called transfer learning. So basically we're going to take a model that is very good at doing one thing, and we're going to use all of that training that it's already had and then sort of slightly retrain it to perform a related task, but that still benefits from its original training, transfer learning. Transfer learning is something that applies to neural networks, but of course also to humans, right? I mean, imagine now you are learning deep learning with Keras. If then you're going to do a deep learning tutorial with PyTorch, for example, another toolkit, then of course you're going to benefit enormously from already having learned everything with Keras, right? So it's also a form of transfer learning. Or if you're learning Italian and you've already learned Spanish before, you're also going to benefit from having learned Spanish, etc. So transfer learning is a very real and very ubiquitous phenomenon. So we're going to start, as before, by importing MobileNet, the network, and loading its weight. So importing MobileNet version 2. And by the way, as before, this tutorial also has a text version of it on python.coxi.nl. So if you want to review the code that we're typing here or just read everything back, then you can go there and watch that tutorial. python.coxi.nl. The link is also in the description of the video. All right, from Keras, we've been here before, right? From keras.applications.mobilenet version 2, import MobileNet. Slight note relating versions. Some versions of Keras, I'm not entirely sure where and when, also allow you to directly import MobileNet from keras.applications. But here, the version of Keras that I'm using requires that you specify it like this. So you will see probably both notations, both forms of import being used, but it just depends on the version of Keras that you're using. And then I'm saying model is MobileNet, right? We want a pre-trained network, so we have to say that the weights that we want is ImageNet. Okay, F9 to run it, there we go, and now we have our model. So what do we actually want to do? I have a very cool, quirky data set. I will load a few images actually. Here, cats. And there are 40 images, F01 to 20 and M01 to 20 of female cats. So the it's view 1. This is a female cat number 1. And male cats. This is male cat number 1. And what we want to do is train our network such that it is not able to recognize that these are cats, but that it is able to tell apart the male from the female cats. Now that's very difficult, right? For me, male and female cats look super similar, so I'm not sure whether the network will be able to learn it, but we're going to try. In any case, it is a task that is quite similar to what it has been trained on, MobileNet, namely classifying images, but the type of classification that we're going to do is very different, right? Or slightly different. It still involves cats, but now we're going to classify male and female cats. So this is a good example of transfer learning. Say that we wanted to, for example, do a weather forecast based on some kind of, satellite images or something like that. Of course, then it would make not as much sense to use MobileNet and then do transfer learning, because then what MobileNet has already learned is probably not very helpful for generating weather predictions. But as long as your new task is a relatively good match to what the network already knows, then you can use transfer learning. I hope that makes some kind of sense. Okay, we're going to start by loading the data and generating the labels. Just like before, remember the second tutorial where we were rounding numbers between 0 and 1? We need to create a data set and labels with the expected output, and then we're going to use that to train the network. What should our data look like? Well, just as in the previous tutorial, it's going to be a NumPy array, import NumPy. SMP, let me make a bit space, data, we're going to start with an empty array, 40 by 224 by 224 by 3. What does this mean? We have 40 images. That's the first dimension. They are 224 pixels high, 224 pixels wide, and there are 3 color channels. That's what it means. Right? In the previous tutorial, we had 1 by 224 by 224 by 3 because we only had 1 image. Now we have 40 images, 20 males, 20 females. Okay, so let's read them in. Let's first actually read in the female images. For I in range 20, we're going to use a simple for loop. And we're going to say, okay, from image IO, import emRead, right? The function that reads an image and returns a NumPy array. And our image is cats / the female, pointer to D, right? So these are they need to be right there. Is this correct actually? Yeah. So it is f01.jpg, not f1.jpg. So they're always two. It is 0 padded, and that's what this means. .jpg. Then we use .format I+1. I'm assuming you're kind of familiar with string formatting, right? So we will use I+1. So for the first image, that will be I will be 0, I+1 is 1, and that will be sort of put in here. And it will be 0 padded so that it's exactly 2 digits long. So it will become f01.jpg. Okay, that's how we read in the image. Now, remember that the image is initially in the pixel values are initially from 0 to 255, and they need to be in the -1 to 1 range for the network, because that's what the network expects. And in order to make that happen, we need to pre-process the input. And to pre-process the input, we've seen this in the previous tutorial, right? So I'm not going into it too much. We can use the MobileNet version 2 import pre-process input function. And then we say IAM for image is pre-process input image. So we're reading it and then we're pre-processing it so that the pixel values are from -1 to 1. Then we need to resize it actually, because the network expects images that are 224 by 224, but these images are not. They're actually their sizes kind of differ. So we're going to use from the scikit image toolkit skimage.transform import resize. So this is one of several functions that you can use to resize an image from one size to the next. And we're going to say image is resize image, and the output shape is 224 by 224. All right. And then we say, okay, in our data, at index I, we assign this image. This is a bit complicated, perhaps, right? But it's kind of doable. We looped through all 20 images. Oh wait, this I should say emRead here, of course. Why didn't you warn me that I made a mistake? emRead, and we're reading this in. Then we're pre-processing the input. Then we're resizing the input until it has the correct shape, and then we assign it. The order of these operations matters. Actually, if you resize it first and then pre-process it, for some reason it doesn't work anymore. So always sort of check at the end of the day that the format of your image, of your data actually matches what you should feed into the model, right? Never assume, always test. I did test. I'm not testing here, but I did before. Okay. Now we're going to do the same for the males. So I just copy-pasted, duplicated it, and then I say up I plus 20. Okay. Now, let's run this. Let's see if it works. Precision not allowed in integer format specifier. 0.02. Oh, wait, sorry. This is not correct. Up. It should be like this. All right, let's run it. Okay, there we go. Right, so I often make mistakes with this string formatting notation, but you will figure it out in the end, right? Okay, so now we have our data. Let's check that it's in the correct range. Data.min should be -1. Data.max should be 1. All right, that looks good. Now, we also need to generate our labels, right? Actually, let's make a new, here I said, let's create a new cell to generate the labels. Generating labels. Our labels can be pretty simple. It can just be a NumPy array, a one-dimensional NumPy array, where the first 20 values are going to be 0, indicating that the female cats correspond to category 0, and the second 20 observations are going to be 1, indicating that the male cats correspond to category 1. So we can say labels mp.empty, 40, dtype is int. So an empty array of 40, and it's going to be integers. Labels, the first 20 should be 0, and the last 20 should be 1. Okay, that's it. F9, let's inspect it. Okay, looking good. So now we have our training data, we have our labels, we have a network, but not a network that is suitable yet for actually doing this training. But before we are going to modify the network, let's check actually if the network as it is, just the pre-trained MobileNet, is actually able to recognize that these pictures all belong to cats, right? There's a sanity check. Generate predictions for cats, cat faces, but this is just generating predictions. So, but this has nothing to do yet with the female and male category, right? It's just the general predictions for cat faces to check if they are cats. So we first say predictions is model.predict, and then we pass the data. Then we need to, as in the previous tutorial, we need to this will generate an array of 40 by 1000 values, with the first dimension of 40 corresponding to our 40 data images, and the second dimension of 1000 corresponding to the 1000 output neurons. And this is not really very readable, so we're going to use the Decode Predictions function to take this and turn it into something that we can read. So we're going to say from Keras, and if that sounded a little bit magical, refer back to the previous tutorial where I explained that in a bit more detail. MobileNet version 2, import Decode Predictions. And then I say for decoded prediction, in decode predictions, our predictions, and now I'm only interested in the top one. So for every image, I just want to have the winner, right? You can, in the previous tutorial, we looked at the top 5. Now I'm just going to look at the top 1. So we will get, in the end of the day, 40 winners, 1 for each image. All right, then for the name, description, and the score in the decoded predictions. Oh, in decoded prediction. Decoded prediction. We print it out and we say print up description dot 2f up %. Dot format the description and 100 times the score, so that we go from proportions to percentages. Okay, this looks pretty good to me. Let's see if we can run it. F9. So it will start to generate the predictions, takes a little while for the 40 images, and then we will get the winners. And they should be cats, right? If the model makes sense, they should be cats. Invalid format specifier up to F. What did I do incorrectly? I again made a mistake with the, here, like this. String formatting up. F9. Okay. All right. Now let's scroll up. So that's good, right? Actually, MobileNet doesn't just know that something is a cat, but it even makes distinctions between various cats: Siamese, Angora, Tabby, Tiger Cat, etc., etc. You see that it's quite often the scores are pretty low. That's not because it's not sure whether it's a cat or not, but just because the top for each image tends to consist of several cat types, with scores kind of distributed across those several cat types, right? Because it knows about so many cats. Actually, I personally wouldn't be able to tell all these cats apart. But for every single image, it actually is correct. Oh, hey, wait, here's a mistake. Lynx. So one, because it's a lynx is a kind of cat, right? A wild cat, but it's not a normal cat. So, okay. All right. But it's decent, right? It's doing with our data what it should do. And these photos are also not ideal, to be honest. So now, but so far we've not really done anything terribly innovative with the model. So what we want to do now is modify the model in such a way that we can retrain it to classify male and female cats. Oof. How does that work? This is where things become a little bit complicated. It's not a lot of work, but it's a little bit complicated. But it is really, we're getting into the core of deep learning here, right? So what we're going to do first is generate a new output layer. Remember that the output layer determines how many categories there are. So the current output layer has 1,000 neurons corresponding to 1,000 categories. We have only 2 categories, male and female cats, so we have only 2 output neurons. So I say from keras.layers import dense. We're going to have a densely connected output neural layer. And I say our cat output. So the output layer for a cat model is going to be a densely connected layer consisting of 2 neurons, and the activation function is going to be softmax. Remember the softmax activation function from the second tutorial, which is basically normal for an output layer, and it basically squashes the activation of the output neurons to the 0 and 1 range. Oof, now, what do we do then? Now things become a little bit involved, actually. There are various ways to modify a model. But what we're going to do is basically take all the layers of the existing model, except for the last one. And then we're going to take the output of that second to last layer, and we're going to connect it to our newly created output layer. Let's actually take a look. Let's print out the model.summary. Okay, so you see here, this is the output layer of the original model with 1,000 neurons. The layer before it is this one with 1,280 neurons. What we're going to do is basically take everything from this layer until the input, so everything above it, and connect that to our output layer that we created ourselves. How does that work? The first thing is that we say cat output. It's a bit strange, this is cat output. We're pretending that cat output is actually a function that we can call. It's not, it's a callable object. It's a bit of a strange concept, but you can call it as though it is a function. And what do we specify? Well, we specify the output of the layer that we want to connect it to. So we say model, that's our original MobileNet model. Has a bunch of layers, and the layers are just like a list. -2 is the second to last layer, right? The -1 would be the last layer, the original output layer. -2 would be the second to last, so the one before. And the output of that is what we're going to feed into our output layer. And then we get something back, which we again call cat output, but actually it is just kind of a weird object called the Keras tensor. So conceptually what happens here is we create a new output layer and we connect it to everything of the original model except the original output layer. What happens technically is a little bit involved and complicated actually. We also need an input. So cat input is the original model input, because that stays the same, right? We use the same kind of input for our modified model, namely images, as MobileNet did. So that part we're not actually going to change. And then we're going to say, from Keras import model, and we're going to say our cat model is a model, and the inputs of that model is the cat input. Oh, I made a typo here actually. It's model.input. And the outputs is the cat output. Oof. Now, So I hope that makes some kind of sense. It is very short, the code here. It is difficult to understand what happens technically, exactly behind the scenes, but it is easy to understand what happens conceptually. Namely, we take the original input, we take the second to last output layer of the original model, we put another new output layer on top of it, and then we take all of that and we put it into a fresh model. That's what we're doing here. Okay, so now we could start first compile the model and train it. But actually, if we would do that, we would be making a mistake. Why? Well, because right now, if we would start training this model, all the weights, all those 3.5 or so million parameters would be trained again. But they're already trained. Really, what we want to do is leave all the original pre-trained parameters as they are and only basically train the last output layer and the connections to the last output layer because that's the only part of the network that hasn't been trained yet. And actually training sort of having part of the network being completely random, which is the case for our newly created output layer, and the rest of the network actually being already trained of sorts, and then sort of training that all together is a very inefficient and messy way of training. So what we want to do basically is freeze, as they call it, all the layers except for our output layer that we added. That sounds very complicated, but it's actually not. We can say for layer in getModel.layers, except the last one actually. And then we say layer.trainable is false. So what we're saying here is loop through all the layers in our new cat model, except for actually the output layer that we created ourselves, and set the trainable argument to false. And that means that when we train it, actually the parameters of those layers will not be touched. They are not part of the training process. Okay, let's run this, see if it actually works. Yes, or at least it doesn't give an error. It's already a start. And now we're going to compile the model. And remember, the compiling is just what we did before in tutorial 2, where we prepare the model for being trained. Compiling the model up. And we can say model.compile, and we're just going to do it just in the exact same way as we did before in tutorial 2. So we're going to specify the loss function. Loss, again, is sparse categorical cross entropy. And remember that if we code our labels with numbers, integers like 0 and 1 in our case, and our output, and we want to actually use those integers to refer to activation in the output layer, such that activity in the first output neuron corresponds to label 0, and activity in the second output layer corresponds to label 1. Then we need to use the sparse categorical cross entropy function, right? So that is basically what tells our model how to map the actual output of the network onto the labels that we're using it to train. If that sounds confusing, go back to tutorial number 2 where I explained that in more detail. And the optimizer, Adam, is the algorithm that adjusts the weight of the model to actually reduce the loss, to reduce the error. And then, so those keywords are necessary for training, but then just so that we have a little bit of feedback, we also specify metrics accuracy, which basically gives the classification accuracy during training when we print it out. Okay, let's run this. F9, okay. And now we can actually start training our model, training the model. And this is the same as we did before. So we can say our cat model. Oh, so I said model.compile, but of course it has to be cat model.compile. Yep. Yes. And now I say cat model dot fit. The x, put it on multiple lines. The x corresponds to our data, right? The y corresponds to our labels. The epochs corresponds to 20, so we're going to train it 20 times on this input data set of 40 images. And the verbosity is going to be 2, so that we can see what happens. All right, let's start training it. Up. There we go. It will take a while, right? We have a complicated model, we have 40 images. epoch 1 out of 20. And then we're going to also track what happens to the accuracy, and it's going to be quite interesting. Okay. Up. You see that the first epoch always takes a little while, and then the rest of the epochs actually go pretty fast. Now, this might be surprising. We see in the beginning, basically the loss is quite high and the accuracy is randomish. But then the accuracy goes up, until basically already in epoch 19, the accuracy is 1. In other words, our model is perfectly able to tell apart the male from the female cats. It's able to classify the pictures into male and female cats. That to me is a bit surprising because they look super similar, right? So what actually is the model classifying here? Now, this is where we should not actually be too trusting of our model. Let's first actually generate a few predictions so that we can see this in a bit more detail. So we're going to generating predictions, but crucially for the training data. So so what we're going to do is say predictions is cat model.predict data, and then we're going to print out, let me see, F9, there it goes. And then we will get, right, just to sort of jog your memory, predictions.shape. What we get is a 40 by 2 array. So the 40 for the 40 images and 2 for the input, for the 40, 2 for the 2 output neurons. And then what we actually want to know is for each of these 40 images, which of these 2 output neurons is the most active. And for that, we can use mp.argmax, predictions, axis is 1. Up. And then it will actually tell us, so for this axis, which of these 2 values was the highest? The first one, 0, or the second one, 1. And then you see that for the first 20 ones, it is all 0, and for the second 20 ones, it is all 1s. And that means perfect classification accuracy. Why? Well, because the first 20 images were actually female cats, and female cats were trained to be category 0. And the last 20 ones were male cats, and male cats were claimed to be should be category 1. So this basically is another way to show that the model is predicting with perfect accuracy, which we already saw during the fitting of the model. However, what we have here is a situation in which we are training the model with very few images, and we're giving it a very difficult task, perhaps an impossible task, I'm not sure. So what might be going on here is not that our model has learned in any meaningful way to tell apart male and female cats, but that it is simply memorized each of the exemplars and remembered whether it is a male or a female, right? And we could do the same thing. I mean, I cannot tell apart male from female cats in general, but if I would have some time to actually study these 40 images, I think I could memorize for each of the images whether it's a male or a female, right? If I just study hard. But that's actually not a very useful way of learning. So how can we tell? Well, there we get back to what we already touched upon in the first or the second tutorial, namely that we need to have a separate validation data set. So we need to take our 40 images and take a subset of it, say 30 images, and use that as our training data set. And then the remaining 10 images we're going to use as a validation data set. That's not going to be used for training, but we're going to use that to see how well our training generalizes to that separate validation data set. How can we do that? Well, let's first actually generating separate training and validation sets. So we're going to say our training data is mp.empty 30 by 224 by 224 by 3. And so we're going to create a training data set of size 30. We're going to create a validation data set of size 10. So what are we going to put in our training data? So the first 15 data points in the training data are going to be the same as the first 15 data points, so the first 15 female images in the original data. The second half of our training data, so 15 and onwards, is actually going to be image number 20 until 35, right? Okay, and for the validation data, it's going to be kind of similar. Validation, except that it's only has 5 females. Which 5 females? Well, 15 to 20, and the males are going to be image 35 until the end from the original data set, right? So we take the first 15 females, assign them to training data, the last 5 females, assign them to validation data, take the first 15 males, assign them to training data, and the last 5 males, assign them to validation data. We also need to get the corresponding labels. So the training labels is an empty array of length 30, and the training labels, the first 15 of those are 0, those are the females, and the last 15 are males. For the validation, it's very similar, right? Except that again that it's smaller. So our validation labels, validation, validation, is actually an array of size 10, and the first 5 are females and the last 5 are females. I hope this makes some kind of sense, right? So this is just a pretty verbose and not super elegant way of splitting our original data into 30 training images and 10 validation images, and also creating corresponding labels for them. F9 to run it. Okay, so what we're going to do now, we're going to train our cat model again. But then of course we cannot train the cat model that we already have because that would be cheating. We're going to create a new cat model, a fresh one. That's why I load this. And compile it. So now we have a fresh cat model. And now what we're going to do is training with separate validation data. And it's very similar to above. So I'm just going to take this and copy it, paste it here. The only difference is that now we're going to specify another keyword, namely validation data. In the second tutorial, we used the validation split that actually automatically splits the data into a validation and a training data set based on a proportion. Here we're doing it a little bit more explicitly by specifying exactly which of the validation labels, training data, training labels. Here we're doing it a little bit more explicitly by using the validation data keyword, but both validation split and validation data are very similar in their purpose. Now let's run it. So we start with epoch 1, right, just as before. And then we will see what happens to our validation accuracy. Does it also go up? And now you see, there we go, epoch 15. You already kind of see what's going on, right? So after 20, we see that our accuracy for the training data is 1. It has perfectly learned the exemplars in the training set. But the validation accuracy is only 0.6. So that's pretty much chance. So what does this mean? It means that yes, our model is able to tell apart which images are males and which images are females from the cat faces, but it does so on an exemplar-like basis, just memorizing for each photo whether it's a male or a female. And the knowledge, the training, doesn't generalize to a new set of cat faces that it hasn't seen before. In other words, this is an example of overfitting, of the model learning the details of the training set without actually learning the general underlying rule. And I hope that now you've seen actually how you can test whether your model suffers from overfitting. Okay, well, we've seen a lot in these 4 tutorials. I hope you had fun. So we've seen now how you can actually take an existing model and sort of take off the top layer, the top output layer, put on your own output layer, and then retrain it for a different purpose than what the model was originally trained for. And that's an example of transfer learning. Now that's where the current set of tutorials stops. But it's only the beginning of all the things that you can do with deep learning in Keras. Perhaps I'll make some more tutorials in the future if there's demand for that. But in any case, the techniques that you've learned in these four tutorials are already enough to have a lot of fun with Keras and deep learning and to do some serious data analysis also. So get coding, have fun, and enjoy. Thank you for watching.